I talked a little bit about integration styles. That may be a bit of a recap of stuff you've heard earlier, but hopefully it'll help frame where messaging sits amidst the variety of integration styles. And then we'll talk about some of the key ideas behind messaging. I'll show you an example of a use of messaging in a task queue. And then we'll look at some .NET code, just give us an idea about how you might do messaging in .NET. And there's a Q&A section towards the end. Okay. All right. So what do we mean by a synchronous conversation as opposed to an asynchronous conversation? So in a synchronous conversation, both parties must be present for communication to succeed. And the way I tend to think about this is a phone call, right? I pick up the phone, I call somebody, I talk to them, and we're both present having a conversation at the same time. Both of us need to be active there. Nowadays, the only person that phones me is my mum. Everybody else uses messaging. We'll come to messaging in a second. But typically, these are things like OpenAPI, GraphQL, gRPC. All these things require both the client and the server to be present at the same time for the communication to happen. By contrast, in an asynchronous conversation, the receiver does not need to be present at the time the sender communicates with them, right? They use some form of store and forward to pick up the message later. So the mailbox icon here gives a hint as to how this kind of works, right? I take a letter, I put it in your mailbox, you come home later, take it out of your mailbox and you read it. Don't need to be present. And the modern equivalent of this is WhatsApp, Messenger, Telegram, whatever your favorite choice is. And the reason we all do that in preference to making phone calls is it's just easier, right? I don't need to actually make sure that you are around when I want to have a conversation with you. It's frustrating if I try and have a conversation and you're not there. Right? So snail mail is the classic example on the messaging. And then there are lots and lots of protocols. You may have heard the names of like SQS, Kafka, various flavors of MQP, MQTT, etc. There's different ways of doing this conversation, right? S3 on the end is interesting, right? But that's actually a file system of some sort. Why is that an asynchronous conversation? So we'll come to that in a minute. But that's the key thing. Are both parties required to be present is really what we're talking about. And sometimes I find people get this a little confused with, particularly .NET developers, seeing having an async keyword, where async really means, hey, hand this over basically to the event loop in order to basically allow my program to continue while I'm doing some I/O. And that you can therefore do a kind of synchronous conversation, right? I can make an HTTP call to you and, hey, I'm async, right? But actually your conversation is still synchronous. The other party needs to be present. You just allowed your program to continue while you're having that conversation. You're just doing you're having that conversation, but at the same time you're browsing basically the internet. Right?
Would you also agree that as a sender, I don't even need to know where the receiver is? Like, I don't need to know what's the space in which they live.
Right. So yeah, I mean, there are definitely ways in asynchronous conversations of doing this kind of pub sub model, which says, hey, actually, I'm going to send it to, say, the post office, and it's going to send it out to all the houses in a certain area for me. So I definitely get that kind of model as well with this. Yeah. And we'll talk a little bit about that later, how you can insert steps in between. Cool. We also carried a bit about this idea called behavioral integration. So with behavioral integration, the receiver exposes some kind of API, parameterized method calls. And interaction is usually this kind of request response spec. The way I tend to think about this is nowadays, quite often when you want customer service of some internet-based business, you may effectively find that you're dealing with some kind of bot that you're interacting with, where you're saying, hey bot, basically I didn't get my order. And then the bot asks you a question, you respond, it asks you another question. We have this very tight kind of integration going on. Later, I seem to remember I've seen her write bots before on various Twitch streams. So what we say is basically this behavior integration. I am focused on, hey, I ask a question, get a reply. That tailors what response I give you. And you then give me back a response to that, etc. By contrast, there's database integration, and that's really I just send you a lump of stuff. And I wait for your reply, or maybe I don't wait for a reply at all. So this is me sending you your customer service department an email instead, saying, hey, I didn't get the package. Can you take a look at it for me, please? And hitting send. And I probably give you all the details in there of, hey, this is my package tracking number. This is when I expect it to be delivered. I was in, your guy didn't turn up, etc., etc. What I'm doing is, rather than having this interactive conversation, I'm assuming, hey, you're domain experts in doing delivery. I'm just going to give you all this information and you can figure out how then to respond to me and my particular query. So two different styles of interaction, if you like. This kind of like almost send you an email or actually have a tight interaction asking questions. And there are a couple of little dangers to be aware of. So in architecture, one of the things we're always trying to do is minimize coupling. Some coupling is always necessary, right? Otherwise, my computer sits in a basement and nobody touches it. Some coupling is always necessary, but we try and reduce some particularly bad coupling. And one of the pieces of coupling we care about is called temporal coupling. And that says if both parties must be present to succeed, we say they are temporally coupled. The availability of one has the impact on the availability of another, right? If I have to ask Jakob a question in order to respond to you, let's say you're saying, hey, where's my package? And the only way I can do that is phone Jakob and say, hey, Jakob, do you know where the package is? If Jakob's on his lunch break, right, I can't respond to your question about where's my package. I have to say, but we're going to have to wait till Jakob gets back from his lunch break, I'm afraid, and then I'll call you back. And you're going to be a bit of a frustrated customer going, why is Jakob taking his lunch break when I want my package, right?
I must be alive to answer your question. I must be alive, right?
Yes, exactly. So this idea of temporary coupling, that our services can end up in this horrible mesh where availability of one depends on availability of the other. And the way that tends to manifest is things like when you want to release a new version of your service, all the other services are dependent on you. They can't talk to you anymore for a period of time. So your release impacts their uptime. And we also think about behavioral coupling. So behavioral coupling is this idea that when we have this really tight behavioral integration where I'm asking you a series of questions, etc., I very much couple into this workflow, right? So we say where two systems use behavioral integration, they're coupled by the set of calls in the interaction. We can find it hard to change who we talk to. We find it hard to change how we talk to them. So those kind of bots are a really good example. They can't really go off script to try and resolve the problem very easily. We tend to basically be tightly coupled into this kind of exchange, and it's difficult to get out of. And it isn't really part of this deck, but in reference to kind of the earlier talk, one of the key differences between something like REST and gRPC is that REST doesn't tend to basically have this tight integration. It deals with data, a resource, rather than more tighter integration that gRPC would have by exposing its parameterized methods. Okay. All right, so let's look at some integration styles and let's see how they fit into this classification scheme we've given. So first one, the oldest kind of one in the book is file transfer, right? Producer writes some data to a file, so a process or an application says, I'm going to write some data to a file, and later on another consuming application comes and reads data from that file. This goes back to mainframes, right? And, loading tapes onto mainframes that, one writes to, then you take it off, and another one then reads from it, right? But we do this all the time. As developers, when we're learning new languages, quite often this is a common thing for us to do, write something to a file, read something from a file. It's very simple. And nowadays actually gets a bit more of a lease of life because we have these really reliable cloud distributed file systems like S3 or Azure Blob Storage that essentially mean, there's lots of advantages to writing to this really reliable storage. We have to agree a certain number of things to make this work, right? We have to agree what the file format looks like and whether it's binary or whether it's plain text. We have to figure out basically where that file is as well. So you and I are going to have to figure out where are we writing files to? How do we exchange that information about location? Generally, a consumer either has to keep saying, is there a file? Is there a file? Is there a file? Right, which can be puts a load on the consumer to keep checking, or we have to some kind of notification set up. So basically, when the new file drops into that space, I'll get a message saying, hey, there's a new file, and I can go, great, I'll go and read it. And then it can get complicated if we want to start doing scaling, right? Because we have to start saying, well, hang on a minute, is this file, can I read the file right now, or are you writing to it? So who has a lock to the file? Hey, if we want to scale the number of consumers, are you reading that file and I read this file? How does that all work? So that we can rapidly get into complexity of file transfer. So that at some point you may say, this has got more complicated than file transfer can deal with. I want to use a different strategy. We think of this as asynchronous, right? Both parties don't need to be present. I can write to the file, pick up any time, and it's database integration. I'm just dumping a load of data on. Right, shared database is another strategy, right? Producing application writes to a data store, so I'm showing an ORM here, but other mechanisms would be appropriate, and says, okay, I'm going to write my entity to the data store. Other application comes along and then reads that data at a later point in time, right? Very simple. we have to agree the schema. Okay, so we are both coupled to this schema. You can think about this as a form of behavioral integration, if we like. In other words, if you change the schema, I am impacted. And that tends to mean if you want to change the schema, both you and I are going to have to be re-released. So that ripples the changes out, and that can be a problem. The other problem is this can be a scaling bottleneck, right? If that table, essentially, lots of people are reading from it, and even most people are writing to it, we may have trouble scaling. Now, typically what tends to happen if we have too many readers, we then have to create read-only replicas and effectively read from the replicas instead of basically the master. And if essentially we have too many writers, we have to then partition our writes. And we do get eventually cloud scale things like Cosmos and Dynamo, which can help us. But busy tables can become a bottleneck to those schema changes. And finally, we can find it's quite difficult to create these unified schemas. If everything is talking to the central data store, one schema that meets everybody's needs can become hard, and we end up with abstractions. And the developers say, I've got to translate from my model in my software of what's happening to this abstraction that someone's created based on data store. And back in the day when we used to do this a lot, I remember dealing with things like a party model, which was basically an abstract description of somebody you were talking to, but you wanted to actually know you were talking to like an insurance broker or whatever. But as you had like enum types and things like that, quite hellish in the end. And generally we can think of these as they're asynchronous, don't have to be present at the same time. They integrate data, but they basically have a form of behavioral coupling, even though there's no behavior interaction because of this schema coupling. Mm-hmm. Write procedure calls. All right. So the client effectively says, I'm going to call a method. It turns out the method isn't local to me. It's actually on the server. And what tends to happen is I have some stub. Quite often my framework would generate the stub for me, which translates what I think looks like a local call to me into a network call. On the far side, I've got some kind of proxy that effectively does the same job, takes this network call and makes a call to a procedure running on the server. So things like WCF, gRPC, all kind of work this way. Typically, we have to have some form of service discovery so that the client knows where to find instances of the server. That's typically some kind of a key value store. Things like console come here. It's part of what a service mesh will do for you, etc. There are two kind of options. One is the server says you have a session, and I maintain state, so you can keep making calls to me, and I'll preserve state between those calls, or you're stateless, or effectively where you say, okay, in between, the client has to maintain all the state, and essentially you just have to pass that back and forth each time you make a call. It's a synchronous conversation. So both parties need to be present for it to work, and it's behaviorally integrated most of the time because we're making function calls. It tends to be very chatty. And that leads to us having both behavioral coupling and temporal coupling in the right procedure calls. Finally, messaging, which is what we really want to focus on a lot more today. So what happens in messaging? So what happens is I write a message to what we call a channel. We'll explain some of these terms in a bit more detail as we go forward. And the consumer reads from a channel. So it's very similar in a way to the way file transfer works, right? I write some data, you go along and read that data later. And again, a bit like file transfer, we have to agree basically the content type. Am I sending you a binary payload, a plain text payload, and the format? What schema is the message? Do you expect to be able to read this? You must understand the schema of what I'm sending you. And then we have some kind of messaging middleware that you're going to read off. And essentially, we get a choice between kind of polling that or receiving a push notification. So again, a bit like the file transfer system. And then we may also, if it's like file transfer, want the middleware to provide some means of saying, hey, I want to scale this by having multiple consumers reading that. So can you lock messages that are being already read by somebody, etc. Right. So middleware, in some ways, messaging middleware, you can think of it as solving a lot of the problems that file transfer has and effectively making a version of file transfer that you can use with all those kind of like little cases as you begin to scale it up solved for you. It's an asynchronous conversation. We integrate by data. I'm sending data across the wire. Okay. And we can overall think about these trade-offs in this kind of diagram, right? So in the bottom axis, we basically got thinking about whether we are coupled to behavior or data. Data is good, behavior is bad. And in the top axis, we're thinking about whether we're an asynchronous conversation or a synchronous conversation. So these old school N-tier applications that basically use SOAP and gRPC to communicate, their problem is they're both synchronous and they're coupled to behavior. Whereas when we look at something like messaging, this kind of event-driven model that's in the top right, what we're saying is we're coupled to data and we're asynchronous, which gives us a lot more flexibility. So that's why we want to basically encourage people to not just basically position themselves in the bottom left using gRPC and REST, but start thinking about positioning themselves in the top right. And particularly if what you're doing is building microservices. Microservices are all about independent deployability, being able to work as a team independent of other teams. The more you use something in the top right, then the more independence you have of everybody else, because you're removing those couplings at basically not just effectively at design time, but also at runtime.
So the top right differs from the top left also in intention, would you say?
Yeah, so what's command driven? So command driven is quite often where we are asynchronous, where I intend to basically send you something by perhaps messaging middleware. But quite often what we're doing is saying, this is a specific message, this specific service, where I effectively expect to get quite often a reply back from you. So what I'm doing looks a bit closer to kind of that RPC style communication. I've got a bit more behavioral coupling. Whereas a truly event-driven says, I just broadcast my thing into the ether, and it's that pub sub model of, and somebody subscribes, but I don't really know who they are. So I'm not even coupled to their existence, right? I just do my work, and provided I produce my message, everybody else agrees. I've done enough. I'm good.
Got it.
Okay, so let's talk about some key concepts in messaging that you need to understand if you want to start adopting messaging, right? Okay. So don't worry, we're going to walk through this diagram, explain kind of what this means. The symbols, by the way, come from someone called Gregor Hope, who basically wrote a book called Enterprise Integration Patterns, which a lot of people think of as the Bible of kind of messaging-based systems. So starting at the left, I've got an application. And the first thing to think about is gateway. What's a gateway? Well, I probably want to separate my domain code from my messaging code. So the gateway just says, hey, I'm going to abstract behind some kind of interface, something that says, hey, I want to send a message. And here basically is the thing that I want to send. Please, can you send it for me? Our messaging gateway code itself, which basically separates our lovely domain and application code cleanly from the code which to send messages, will tend to use a local SDK for whatever messaging middleware we have. So we think about there's the channel adapter. So you may have different messaging frameworks like Kafka. If you use something like SNS, you may be talking an HTTP variant, which is semantics over HTTP. If you're using like Azure Service Bus, you're talking AMQP. There are different protocols. So quite often we have a little client SDK. We've got it off in .NET terms. Got a NuGet package we downloaded, and that's what our gateway is actually using to talk to the messaging middleware. And then effectively using messaging middleware, so some messaging product, we're going to send stuff over to basically be consumed by our receivers. And we tend to basically be sending a message, which has basically both a header, which is very metadata about the message. It says, hey, things like, what's the identifier? Hey, is this plain text or binary? What's the schema going to be like? What version of the schema am I using? All those kind of things that help us process a message. And then the body, the actual thing that you care about on the far side, reading in the domain code on the far side. So generally, header stuff I tend to think is probably being dealt with in the channel adapter or the gateway layer. They're the things that want to interact with the header. And the body is stuff that the application on the far side wants to deal with. We send it over a channel, right? This is a messaging term for what we think of as a virtual pipe. What I mean by virtual pipe? What we mean is generally what you do is you address a channel by name, right? Sometimes called a topic or a routing key. And you say, hey, I want to send to this channel, please. And anyone who wants to listen says, can I listen on this channel, please? And you don't need to know about details of, TCP IP connections, everything else. You just need to know, hey, I'm listening to this channel, right? And then so effectively you read and write from something that you both agree the name of, right? And then we get this model we talked about earlier. It can either be pull or push. I'm either polling the channel and saying, hey, is there anything new? Is there anything new? Is there anything new? Or I get push. The channel basically, I register the channel and say, hey, when there's something new, can you tell me? And when the channel gets something new, it says, okay, hey, I've got something new. Here's a message for you. And you get pushed to you, right? There are trade-offs, right? But we might not get into those today. It's not necessarily enough time today to get into those kind of trade-offs. Okay. And collectively, we refer to this idea of this channel adapter and gateway quite often as an endpoint. You may hear that term endpoint floated around. The endpoint just means really the bit of your code that talks to the outside world, rather than the bit of your code that's inside and actually goes through the automatic logic. Okay, so it gets a bit more complicated, don't worry. So this is kind of the same diagram, right? But all I've inserted is I've slapped these little green boxes in the middle. What's that? That's basically a broker, right? So we can think about the fact that typically middleware often comes with a broker. So Kafka is a broker, right? RabbitMQ gives you a broker, basically called an exchange, right? As your service bus gives you a broker. So what a broker does is effectively help us separate knowledge of the sender from who the receivers are in many cases. So sorry, that's a bit tiny. So typically what happens is when we talk to a broker, we have some kind of connection to the broker that basically is an input channel we can think of. And quite often, that's just a simple TCP/IP sockets connection. We don't have any kind of queuing or anything there. We're just saying, hey, broker, here's a message. And the broker gets hold of that message. And then what it does is it says, okay, I'm going to send it, and we'll talk about what the broker's doing in a second, to output channels. And those output channels are what we think of as queues. They tend to have what we call store and forward. In other words, they say, I will keep the message until the person who said they want to receive messages comes along and pulls it out basically and deals with it, right? So that's basically everybody's post box. And in the middle is the broker. They're kind of the post office in this equation. And what they're saying is, okay, I'm going to give this message to anybody that tells me they're registered to receive messages under that particular topic or routing key, whatever your platform calls that in the name of it, right? So I might say, hey, I'm interested in messages from Jakub about failed orders. Okay. So I, on the right-hand side, as a channel, would say, okay, I want to subscribe, and that's the control channel at the bottom. I talk to the broker and I say, hey, can you give me many messages rated on the failed orders topic? And we may agree, here's a queue where you'll put those messages. Then I can read them at my leisure, and I get, effectively I can say, okay, every 200 milliseconds, I'm going to poll and look for failed order communications, right? Yep. And then what happens is Jakub basically, in his application, he just sends something onto the middleware saying, hey, I've got a failed order. I'm going to basically send that to the broker. And the broker says, right, who has registered to receive that message? I will route, that's what the router does, I'll route that to everybody there. So if you're used to basically dealing with the web, and you're used to the idea basically of having a router where essentially you say, hey, I get an incoming HTTP message and I'm going to route that to handlers. It's a bit like that. We're thinking in a similar way. We're saying, hey, there's an input channel coming from basically one application, comes to my messaging middleware, and I then basically route it to anybody who said they want to receive those messages, and it goes into their queue, which then means it waits for them to come and receive whenever they feel like it.
And I guess in some brokers, and I think you talked about this at the beginning of your talk, successful delivery and acknowledgement by all of the receivers is destructive to the message itself. Whereas in different brokers, I can have a retention policy, right? You talked about this at the very beginning.
Yeah, exactly. Yeah. Okay. So here we are. The diagram is even more complicated, but don't panic, right? So one of the things to bear in mind about messaging is even though here we are basically at 1 with the application, Jakub sending me a message, right? And I'm 8 over here basically wanting to receive something about failed orders. There may be an arbitrary number of steps in between that get inserted that I as 8 as the receiving application don't need to know about, right? But Jakub may realize, or someone else may realize, they need to configure some stuff to make this succeed. So one, Jakub sending a message basically, it's going to my router, right? And my router's saying, okay, there's a failed order. But actually, the subscriber to failed order, Jakub's message, is actually a channel at 3, which says, well, you've only got the order ID here in Jakub's message. You're going to need order details. So this icon represents what we call a content enricher. So it says, I'm going to go away and get the order details that Ian's going to need basically to help process that order. So it then puts them into the body of the message. You may create a new message entirely with those details. It then raises that up, and that then goes back to the router, right? And that could come to me, but actually in this case, what Sis and I are going to say is even that failed order with details, as we might call it, message, I don't subscribe to that either, because in fact, It turns out I haven't updated my my software yet to receive Jacob's new failed order message with details. In fact, I've got some older version that has a different structure. So we have a translator that steps down that message to format I do understand. So I understand failed order with details V1, not failed order with details V2, for example. So essentially, the message translator translates that message to the format I understand, goes back via the router, and that's what I actually listen to. And one of the big advantages of messaging is our ability to build what we call a pipes and filters architecture, where the data source and the data sink, we can insert these arbitrary steps in between. And if you think about, Web API, where you've got middleware between your handler and the message coming in, where you receive it, for example, an API calling your own code, and you can say, hey, I can do all these things orthogonally I need to do. It's exactly the same in the kind of flow. We get those same advantages of being able to insert all these steps in between.
Would you say that, on the other hand, we have some disadvantages, like it becomes a little bit harder to follow the actual process of handling failures in orders, right? I don't know, as a developer, who gets what and what gets translated to a different message, right?
Yeah, so it can be a little bit harder when we have messaging to reason about what's going on. And that's one of the challenges most people when they first have messaging is, what do I need to reason about? And one of the things we have to tell people is, well, you need to reason about the fact that you send a message and you fulfill a contract. And the other person has to reason about the fact that I receive a message according to this contract. Somebody may have to reason about, oh, how do I make that actually happen? Because these two bits are in between, and I'll be to translate that. But you need to try and focus less on the end-to-end flow and focus on what you need to know in order to avoid a kind of paralysis of, I don't know everything. But yeah, great question. All right, let's talk briefly about message pumps. I'm just conscious of time, so we're after this. But one of the key ideas then for a receiver we saw is this idea of how do I get messages out of the queue, right? So I'm going to process. So message pumps are something, if you want to write messaging yourself, you're going to have to figure out how to do, right? Explain why you might not want to do that in a second. So generally, all message pumps follow the same kind of model, right? Which is I go and get the message. It says basically either it's pushed to me or I poll for it on the queue. When I have that message, I need to translate the body of it into something I can understand. Presumably the body may be in some kind of format like JSON or XML, perish the thought, maybe binary format messaging like Avro. And I want to turn it into something that I can understand in my code, so my type system understands, right? Then I tend to dispatch it. So I don't want to basically have my messaging code everywhere. What I want to do is send it to some kind of handling code that you've built that essentially says, hey, I'm the domain code and I know how to respond to that, right? So typically what happens is I dispatch it to a handler, which you've registered with me, that says, okay, when you get a message of this type, run this bit of code to process them. And then we handle the message. We may get errors. I won't go into depth in these today, but effectively you can get failures to deliver. In other words, the messaging system doesn't manage to give you a message. It sits there in the queue and eventually the messaging system says, I tried to deliver, I gave up, and it goes with the letter channel. Failures to translate. So you may fail to translate the message. It may turn out it's a perfectly good message, just not for you because there's a configuration error and someone sent to the wrong topic. We don't want to throw those away. So we tend to put them on what we call an invalid message channel. We say it's probably actually useful for somebody, or I haven't upgraded my software to understand these messages. Rather than throw it away, let's put it in a channel where we can recover it from later.
Which brings us to a statement about failure handling, I guess. That's not a question, it's a statement, but I think it relates to what you just said.
Yeah, exactly. So we'll talk about failures in just a second. So we dispatch a message. If basically I get a message and you don't have a registered handler for it, generally that's an error, right? Probably you've configured your app wrong, and we'd probably basically shut your app down and produce something to the error log that says, we don't seem to understand how to receive these messages that you're being given, so maybe we shouldn't be configured this way. And then when we're handling messages, then really those are application errors. But there's an interesting thing we can do, right? So in a lot of cases, when we handle those errors, they're unrecoverable, right? We look at it and we say, it's not based on some time-dependent situation. I'm just going to log that. I couldn't fix that, and we'll do whatever we do normally with basic application errors. But the interesting thing that messaging can do for us is in some cases that error may be recoverable because we think if we retry it, so we're talking some downstream dependency that's not available right now, because if we retry it, we may be able to essentially get it to work later. Now, typically we do a local retry first, but if that fails, sometimes what we do is say, let's put that back on the queue. Let's put that back on the message queue and essentially handle that later. And so that lets us effectively keep the work without necessarily consuming, because we've lost a downstream consumer. And sometimes we can use the strategy of saying, hey, we get enough of these, pause reading messages for a while, wait and then resume reading messages so I don't consume everything on the queue. The work is safely waiting for me. I couldn't deal with it right now. Be aware, typically what happens to avoid what we call a poison pill message, a message that we really can't process even though we think we can. We typically set a limit on the number of requeues, and then we put something into better queue saying we can never deliver that. We're worried it's poisoned. So writing this kind of message pump is a key part of what you do in messaging. All right. I'll move over that one in a second. I'm going to skip over task queues just because of timing, because we had a bit of a late start. As an example, I want to get into some of the code stuff. And if we get a little bit of time towards the end, I'll come back to that.
All right.
Let me just focus on the next section, and then we can come back to that if we need to. So typically, what might you write here in terms of .NET code, right? So let's talk about a simple framework. Now, this is not code that you should ever actually really use. It's just basically an idea of what you might then have to write, basically, at a simple level for messaging framework. So in order to basically read stuff, your message pump tends to look a little bit like this. It's a very simplistic idea of it. So you're saying, well, I need to create some kind of thread. That thread is essentially going to read from basically my message queue. When we're abstracting this, you can see on line 6 with the idea of a channel. We're saying, well, we're reading from a channel. Right. Behind that channel, effectively, is essentially like my wrapper around basically some channel adapter SDK code from that particular platform. We'll see that in a second. I'm just abstracting and saying, here's a channel I'm reading from. And then I do this loop, right, basically, which is the message pump, right? And effectively, it's a while loop that just says, okay, try and get something off the message queue. When I do get something off the message queue, translate that, right? Then pass it over to whatever handler I've got registered. This is just very simplistic code, so I'm removing lots of complexity here so you can see it. And then maybe pause to avoid spinning. Check if someone wants us to actually stop reading messages by signaling cancellation, right? And then do the next one. And effectively, you spin up a thread like this, and it continues to read messages, right? There's lots of things missing here. There's no error handling. There's nothing looking at basically saying, how do I know this message handler is for this message, etc. But I wanted to show you some code that gave you an idea of this is kind of almost like the simplest pump you could write, but it's missing a lot of those features around error handling, except you need for genuine messaging. Okay. Now, don't worry about the fact you can't read most of this code. The idea is to just show you kind of the sort of complexity you're dealing with. Inside your channel is where you actually deal with the kind of SDK, right, for that particular messaging middleware. So here you can see what I'm doing is just roughly, don't worry if you can't really follow along. In about lines 3 to 6, I'm really just actually connecting up to the RabbitMQ, this instance basically is middleware, and saying, hey, I want to basically create some stuff that I'm going to need. And then you can see I create some names, etc. But if you go down to line 14, I'm essentially creating a routing table. That's one of these changes in RabbitMQ and saying I need to create a routing table. And then I'm basically in lines 21 to 22, what I'm saying is I want to listen in that routing table to things that have this identifier, right, which is basically the routing key. And if you get something that's sent with that identifier, put it on my queue. This is the queue I want to use. That will store the message so I can get to it later. And then we can do some stuff as well. We declare basically a letter queue to say effectively, hey, in the event of delivery issues, post it here instead. Right. Don't write the detail, just to see there's quite a bit of code. And then we can write something as well that basically says how to actually do that receive operation in the channel. So here again, this is just showing you RabbitMQ. I'm doing some kind of get operation. I'm getting a code back, and then I'm acknowledging receipt. Actually, you don't necessarily want to do acknowledgement like this. What we're saying here is take it off the queue, immediately acknowledge, which means nobody else can ever process it. Generally speaking, a better strategy is to try and handle the message. If you fail, you may want to basically make it available for other consumers, or if your processor to crash, then somebody else could pick it up because you haven't finished doing the work. And again, don't worry about the detail here, but we'd have to write some code, deserialize, and there's some code here which basically says, hey, I'm assuming you've got some kind of deserialize function, and I'm going to actually deserialize the message for you, right? So there's quite a lot of code to write to do messaging.
Would you agree that these examples of code, these are part of message channel adapter? Coming back to your slides from
so basically this is the gateway. Some parts of it the gateway, and some parts of the adapter. I tend to think of the adapter as being the sort of RabbitMQ code you're seeing in here, and this my channel is my kind of gateway of tracking that, right?
All right.
But the key thing that basically you care about is, you want to write this handler, right? That's where your domain code goes for this message. So the advantage of using frameworks, now Bryce is just one example, it's one I happen to work on, but there's also things like mass transit in the .NET space, there's end service bus, there are quite a few, Rebus, there's quite a few out there, right? Is we take away all that work of writing message queues, of writing basically effectively your messaging gateway, plug into channel, and just say what you really want to write is that handler code, the domain code. You want to receive a message and then just act on it. So effectively, you want to fill in one of these, and you can think of these a bit like when you write a controller in a web application, right? It used to the idea of I've got some HTTP in, it's turned basically a post or whatever into a call to me, and it's given me some parameters. That's exactly what we want to do in messaging. You just go and write what we call a request handler, right? In the top line, in line 1, you can see I've derived from basically a base class, and I've created my greeting made handler. And then I've got a key method I need to override saying handle this message, which is basically the greeting made message, the first parameter. You can see I'm returning something that basically says, calling the base class. Why is that? Well, effectively, what we want to do is create a middleware pipeline. So you can put middleware ahead of this message. We'll see basically how that manifests itself a bit later. And then really to that handler, I start to add complexity. So here I'm going to say, in order to handle that message, I've got some dependencies, right? I want to basically, I've got some entity gateway. I want to talk to the database by entity framework core, right? Great. So I'll wrap that basically and give that to myself here. Postbox, talk about in a second, but essentially I want to basically make sure, I want to send a message myself. So when I've received this message and done some work, I'm going to actually raise an event myself to other people. So how do I raise a message myself? This command processor lets us do that, right? Okay. Having done that, we're getting to more complex code, but don't worry, I will walk you through the bits you need to understand. I can then handle that message. Now here, we're just doing some typical thing that you might do. There's a little bit of complexity around that outgoing message. So in line 8, what I'm saying is begin a transaction. In line 11, I'm saying, hey, I'm going to create an entity based off the message I've received. So I'm saying, hey, you sent me a hello world is what it's actually doing. This is an example. You can find an example in our samples of a Brighter. And I'm going to record that I received this greeting. I'm going to add it to my list of greetings that I've received in line 13. And then what I do is I say, I want to send a message, but we do it in 2 stages. And I'll explain why in a second. We put it in what we call a post box. And we say, hey, put the message outgoing message I want to send in there, right? Which says, I received a greeting. Right? Very simple example. And I add it into my list of posts that I've received. Then what I do is I save my changes to the database, right? So I say, hey, go and save my new salutations entity. And what this is doing behind the scenes that you can't see here is also saving it to that post box, right? So both my entity change and my post box get written in the same transaction. So if it failed, I don't have a message in the post box. I don't have an entity, which is what happens in that exception line. If it succeeds, I then clear the outbox. I then say, hey, send the message, any messages that are outstanding. Now, sometimes, of course, what happens is in which we say posts here is I might have many things that I'm doing that create a number of messages to send downstream. So effectively, I let you send more than one. We also, by the way, in Brighter, let you not do clear outbox manually here. You can just put them in the post box and you can set something up that runs in a thread in the background that every so often just clears any messages that are pending. The price of that is slightly more latency because you have to wait to the next clear. This gets you the lowest latency, says do it immediately. But the key point is not the detail here. The key point to understand is what messaging frameworks, and others are the same as ours, try and do is let you focus on writing this handler in the same way when you basically do the web. What you're focusing on is writing a controller rather than getting into the nitty gritty of I've received an HTTP request and I want to turn that into something that calls my code. All right. The attributes at the top on lines 1 to 3, that's just middleware, right? So remember we had that line earlier, we were saying, hey, return, on line 17 here, we said we were calling the base. That's to say, hey, there could be stuff after this. So we're not terminating the call yet, we're passing it on to the next handler, right? And what we've got here by attributes, we'd let you, there's some off the shelf middleware we give you, and you can create your own. What we're saying here, for example, is use an inbox, the top one. So what we're saying in the inbox actually is you could receive a duplicate message. So if we're going to check for that to make sure we haven't seen this one before, and we're going to basically reject it if we've seen it before, right? Request logging, that just says log stuff, basically, so we know what's going on. And use policy async, what it actually says effectively is we're going to use a poly policy to wrap this handler so that we'll automatically take the action that poly says if you throw an exception out of this handler. So that will let us retry this handler, for example, in the event that it failed. Right?
So thanks to this, I can effectively have exactly once processing, right? Without having me to worry about it.
Yep, exactly.
Cool.
All right. So what we'll show you a little bit, so not to worry too much because it's quite specific. So just get the general impression as what's important. Generally, most messaging frameworks, what happens is you've got some usually extension methods in .NET land for host builder where you can add stuff. Here you can see us setting up a subscription for RabbitMQ. We're saying effectively, there's some detail about the subscription we need about what we're going to call the name, we're going to call the channel. The routing key on line 6 is the important thing. That's the topic in the broker that gets us to get stuff routed to us, right? And then we're setting up where does Rabbit actually live so I can talk to it, etc. And then there's a whole set of options here, which you don't have to worry about too much. But really, the line on 911 is an interesting one, right? We're saying, hey, when we send messages, we want to send them externally over basically this bus, which is provided by Rabbit, right? And we do have an alternative being of sending messages internally inside my app, right? We're saying, hey, send it externally. At line 28, basically, auto from assemblies is just saying, find all the handlers that I've got in my application and register them as targets for those messages that I'm receiving out there. Okay. All right. So let's just show you in detail. So most of them will have some configuration you have to do, just like you have to configure, web applications, etc. And that's probably it. Yeah. Okay. All right. So I think probably we should do some questions. The task queue example, by the way, don't worry about. That's just really showing you an example of a way of using messaging. Task queues is a common one. I will probably share the deck at the end, and you can have a look at the slides, and you can see that example. But maybe we should do questions, Jakob, if we've got them instead.
All right, thank you. I have a question, actually. Does Brighter come with some support for testability? Like, can I easily test my code if I receive a message, then a different message is sent out to a different channel, things like that?
No, interestingly enough, we don't really have a kind of a testing framework. What we tend to do whenever we use it is really just write tests against the handler. So the handler can be instantiated just like any class, completely in isolation of the messaging framework. And so we tend to basically test, hey, I push something in, it's going to run some behavior, and then I basically test what I can test effectively the contents of a post box, whatever. And people tend to use some kind of fake there, then basically for their anything that's outgoing, basically pick it up. But we don't come with any extra support out of the box to make that happen. We just tend to let you run those handlers completely independently of the framework.
All right. So the system under test is actually the domain code, not the message adapter, right?
Yeah, exactly. Yeah. So we'd recommend doing that. Obviously, you may want to spin it up and check it all works. And generally what we tend to find is that most of the errors you'll see are configuration errors early on. So you can turn up the diagnostics to get a lot of logging, and we'll tend to give you a lot of information. And generally, you'll find your way battling it early on with a few config errors. You're not pointing to where Rabbit actually lives, for example. Effectively, you've not configured a subscriber correctly. Once you get through all that, generally, we've got tests that test Brighter itself. So you can kind of rely on us to work, and then you go to just go and test your handler actually works.
All right, cool. The code samples you showed RabbitMQ, and sorry if I didn't get that. Is that the only option right now, or can I connect to basically anything?
Yeah, so I mean, we don't manage to do everything, but we do quite a few right now. So Rabbit we support basically Azure Service Bus. We support AWS's SNS and SQS. Those are the ones that are, if you like, the most mature processes that we have. We also support. There, Jakob's still here. He seems to have vanished. Maybe he's dropped off. There he goes.
I don't know what happened. Sorry, that wasn't me. That was Layla, I guess.
We support basically Azure Service Bus, AWS SNS, and SQS. We support RabbitMQ.
Cool.
We support Kafka. There is a PR in from someone I know to put MQTT into our support. Generally, there's fairly easy to write a transport for Brighter. What we tend to want to do is make sure that if we're going to have one as a kind of advertised transport that we support, is have a contribution from someone that's actively using that, rather than us writing one without having people actively using it. You could write one of your own for most transports fairly easily, and we know there are some out there that we haven't written, that people have written themselves for, and we'd encourage people to contribute them back. But in some cases they can't, because they have internal rules that stop them from being able to, contribute to open source projects in that way. But yeah, we cover most of the main ones there. But yeah, if there are particular ones people are really hungry to have, then talk to us and we can see if we can work out a way of supporting them. And we're always happy to work with you. If you're like, one of the ones on our radar is NATS. So let's say you're doing NATS because you're on a Kubernetes environment and you really want a NATS version of Brighter, talk to us, because what we could do is write the first version for you, give it to you and say, please go and test this for us. And once we get it all working, then kind of say, great, we're happy this to kind of go out of preview release to be something we say is now generally supported.
Correct me if I'm wrong, but I could actually test that without having to change any of the event handlers, because my domain code is agnostic to the broker.
Yeah, and you can switch them effectively. So you could say, I'm going to run it on RabbitMQ locally, and then I'm going to effectively actually now test against AWS. Now, we wouldn't take to recommend that, but you can do that kind of thing.
Nice. We do the same in Spring Cloud Stream. It works in the same manner. That's a nice idea. It looks like an ORM, right? But for messaging, so it abstracts away the actual database.
Right. Yeah. Exactly. It's the same kind of principle that you want the developers to better focus on domain code while they do messaging. Now, it's useful to understand what it's doing under the hood, right? It's useful to know it's got a message pump. It's useful to know those kind of details at a high level. But it's difficult code to write and get right. You have to do a lot of testing. You have to test things like network partitions, that kind of thing, etc. And if you really want to see what we have to do that, you can go look at our source and you can see our message pump quite clearly, and you can see all the stuff we have to do to handle various different scenarios across basically any of the frameworks that we support in order to try and keep your messaging going and alive in the presence of networking errors, etc.